We've been talking about homomorphisms in our last couple of videos, and in our most recent one, we gave some examples of some homomorphisms, one of which I would like to go back and study a bit more. You may recall our example of the two groups. Let's see, we looked at these as Z8 cross C2 and Z4 cross C2, and we made those connections as follows. If we pay attention to the numbers that are on each vertex here, we notice that the permutation, which sends position 1 to position 2, 2 to 3, and so on, generates the 8 rotations of the octagon, and does so by identifying each one with a permutation. And so 1 goes to 2, 2 goes to 3, and so on, generates the set of rotations. And if I combine that with a flip that interchanges 1 and 8, interchanges 2 and 7, and so on, then we get a group that's isomorphic to Z8 cross C2. However, if we paid attention to only the letters, instead of 8 numbers, I've got 4 letters, and those are being permuted. So that rotation that's set in 1 to 2, 2 to 3, and so on, also sends A to B, sends B to C, C to D, D to A, and so on. I actually have 2 copies of that. A goes to B can be read over here. A goes to B can be read over there. And we identified a function that went in between the groups Z8 cross C2 and Z4 cross C2. It was a natural function. So we sent the identity permutation in Z8 cross C2 to the identity permutation in the letter group, which I'll designate that way. But I also had another element that went to the identity in Z4 cross C2, and that would be 4 rotations. Let's look. 1, 2, 3, 4 rotations also brings us to the identity permutation in Z4 cross C2. And so I'm also going to send that. So send R4 to A as well. Similarly, let's go back to the identity that we began with. A single rotation. Well, let's see, that sends A to B. I'm sorry, it sends 1 to 2, 2 to 3, and so on. But it also sends A to B, B to C, C to D, and D back to A again. So it's natural to send a single rotation to A, B, C, D. But we have another element that's going to get sent to that, namely 5 rotations. So that was 1, here's 2, 3, 4, 5. That also sends A to B, B to C, and so on. So I'll send, I'll define H of R5 also to be A, B, C, D. And so we continued in this manner and assigned each member of Z8 cross C2 to the corresponding member of Z4 cross C2. And we had we'd put that information together in a graphical representation. So what we have here are the elements that got sent to the members of Z4 cross C2. So here, for instance, R and R5 both got sent to A, B, C, D, right? 1, the identity, and R4 both got sent to the identity element in Z4 cross C2, and so on. And we had shown also that that particular function, this was from one of my homework exercises from a couple of videos ago. Preserve the operation. Now in my homework exercise, I was using F's instead of H's, but that shouldn't matter. Think of H in every time you see a function F in this example. So it doesn't matter if we rotated, say, 3 times. Actually, we're going to read from right to left. So if we do a flip and then 5 rotations, and then compose that with 3 rotations, well, turns out that we get a flip, and that got sent to ADBC. But if we looked at what F did to R3 first, and then what F did to R5F, and then did our composition, we wound up with the same thing. So it turns out that this function H that we're defining preserves the operation between the groups Z8 cross Z2 and Z4 cross Z2. So this function that we've defined is a homomorphism. So Z4 cross Z2 is a homomorphic image, right? It's the image of our Z8 cross Z2 group under this homomorphism. So we call it a homomorphic image of Z8 cross Z2. And if we look at the elements that got sent to the elements of Z4 cross Z2, Z8 cross Z2 that got sent to particular elements of Z4 cross Z2, if we look at those as subsets of Z8 cross Z2, then it turns out that each one of these pairs that we have represented in this graph is a coset of the set of elements that got sent to A. It's pretty easy to see that the elements that got sent to A form a group. After all, it's a subset of Z8 cross Z2, and if I combine any 2 of these elements, I get another element in H. So H is closed with respect to the operation, and it's a subset of this finite group. So H is a subset of this group. Turns out that it's also a normal group. And so it makes sense to talk about the cosets forming a group. And what we see just by virtue of where they're placed on this graph, on this Cayley graph, we see that this quotient group turns out to be isomorphic to our Z4 cross Z2 group. All of this hinged on the fact that this set, the set of elements that our homomorphism mapped to the identity in our codomain group over here, in our range group, that this set of elements formed a normal subgroup of this group. And in fact, I had asked you in our last homework to show that that was true in general. So let me recap that just a little bit. So what I've asked you to show is that if I've got a group G1 and I've got another group G2 and I've got a homomorphism between them, call it H, and over here I've got the identity element in G2, I asked you to show that the set of all elements that got mapped to that identity element that set of elements turns out to be a normal subgroup. I'm going to call it K. So the first thing we'd want to show is that K is in fact a subgroup of G1. And then once we know it's a subgroup, we'll show that it is in fact a normal subgroup of G1. All right, so that's what I asked you to do as a homework exercise. It was a very challenging homework exercise, and for that reason, I would like to spend the rest of our time together in this video going through my argument for why that is the case. So here's my copy of that homework problem. So we're starting with a homomorphism between 2 groups, right? So H is a homomorphism. And we're defining K to be the set of everything in G1 that gets mapped to the identity element in G2. All right, so again, the goal is to show eventually that K is normal in G1, but let's begin by showing that it's a subgroup. So what does that mean, right? Since I already have that K is a subset of G1, that means that I've got to show that K is closed with respect to the operation. And then, since I am not assuming that G1 is finite, I'm also going to have to show that it's closed with respect to inverses. So those are the two things I'm going to do. We'll start by showing that K is closed with respect to the operation on G1. So we're going to pick a couple of things out of K. Incidentally, this is my own terminology, I like to call K the vanishing set of H, right? It's what by sending everything to the identity, it kind of sounds like I'm making them just go away. I'm making them vanish. I'm collapsing them all into what I might call the zero in G2. So K, I'm going to call it the vanishing set of H. So I need to pick two things out of K which vanish, two things out of K which H is going to map to the identity element, and I need to show that their product is also in K. In other words, I need to show that their product vanishes under H. I need to show that their product has an image under H that is equal to E2. So that's what we need to show. This is actually pretty straightforward because, well, after all, H is a homomorphism. It's the only thing we're presuming about H. And since it's a homomorphism, doesn't matter whether we do our multiplication in G1 first and then look at the image, or look at our images first and then do our multiplication over in G2, I'm going to get the same thing. But X and Y both vanish under H, right? X and Y are in K. So H of X and H of Y are both equal to the identity element in G2. And if I multiply the identity element by itself, I'm going to get the identity element, right? So X star Y does vanish under H, right? It does go to the identity element. And that's what I needed to know, right? So if I take two things out of K, their product is also in K. K is closed under the operation. And now let's show that it's closed with respect to inverses. So pick an element out of K. We need to show its inverse is in K. So if X vanishes, we need to show that its inverse vanishes. Well, as it turns out, we haven't shown this specifically for homomorphisms, but you may recall that with isomorphisms, isomorphisms send the inverse of an element to the inverse of the image of that element, and exactly the same proof that we used to show that result applies to homomorphisms as well. And so using that fact, what we have is that H of X inverse, well, using that fact, that's the inverse of H of X. But again, X vanishes, right? X is in K. And so H of X is the identity element. Well, and the inverse of the identity is the identity. So we do have that H sends the inverse of X to the identity. Well, that's exactly what it takes to belong to K, right? The membership requirement to be in K is that the homomorphism maps the element to the identity. That's exactly what we've got. We have the K is closed under inverses. And since it's also closed with respect to the operation, we now know that K is a subgroup of G1. Great. Now we need to show that K is normal in G1. So that's what we'll do for the rest of our proof here. So how do you show that a subgroup is normal? Well, by definition, we could show that left cosets and right cosets were equal. That's not going to be the most straightforward way of doing it for this particular result. You may recall, I think it was Theorem 111 in our course notes said that this definition is equivalent to showing that if I pick any x out of G, that x inverse kx, and of course that's the set of all x inverse kx's, where k is in our vanishing set, that that this is equal to k. So this is the characterization that we're going to use to show that k is a normal subgroup of G1. So we'll begin by showing containment in this direction. We'll show that the set on the left is contained in the set on the right by picking an element out of the set on the left, and we'll eventually show that if y is in this set, then y is also in k. But belonging to this set simply means that it's equal to x inverse kx for some little k in our vanishing set. Forgive my multiple notation here for x inverse. Sometimes I write it this way, sometimes I write it with a bar. I should be more consistent with that. It doesn't really matter so long as you recognize that they both mean the same thing. All right, so to see that y is in k, well, what does that mean? Again, membership in k means that that you vanish under h. In other words, that we have to show that h of y is the identity element in G2. Well, since y is equal to x inverse kx, h of y is h of x inverse kx. But again, h is a homomorphism. It's the only thing we know about h. But that's a powerful property, because what we know is that we can either multiply in G and then look at the image, or look at the images and then multiply in G2. But keep in mind, k is in our vanishing set. So h of k is the identity element, right? So h of k isn't going to contribute anything to my product. And so I can write this as h of x inverse times h of x. But as we've just noted, the inverse of x gets sent to the inverse of h of x. And so whenever I multiply an element by its inverse in G2, I'm going to get the identity element. So sure enough, I do have y being mapped to E2, so y is in our vanishing set. Y vanishes under h, so y is in k. And so that's what we've shown containment, that if I pick y out of the left side, it's also in the right, and so the left side is contained in the right side. Okay, so now let's go the other direction. Let's let y belong to k. Let's let y be in our vanishing set and pick any x out of G1 at all. Now, I want you to note that, and it's not going to be obvious why I'm doing this right away, but I think it will become obvious soon. If I pick any x out of G1 and I look at the product x, y, x inverse, and then look at the image, what I'm going to get is, well, again, H is a homomorphism, so I can look at the images of the individual elements first and then do my multiplication. But just like we had above, since y is in our vanishing set, H of y isn't going to contribute anything to this product, right? H of y is the identity element. And so I've got H of x times H of x inverse. And just like above, that's going to give us the identity element. And so this product is in our vanishing set, right? So there must be something in our vanishing set equal to that product. Well, what that means is since this product is equal to k, I can multiply, let's see, if I multiply on the left both sides of the equal sign, if I multiply on the left by x inverse, and then I multiply on the right by x, what I'm going to wind up with is, well, y is going to be all by itself over on the left-hand side, and I'm going to have x inverse kx over on the right, which is in the set x inverse kx. Well, that's exactly what we needed. We started with x being in k, and now we have that implies that, y is being in k, and that implies that y is in x inverse kx. Well, that shows containment in the other direction. So k is a subset of the set x inverse kx. And since x inverse kx also was a subset of k, that tells me that those two sets are equal to each other. And that's exactly what we needed. So by that characterization of normality that we had in Theorem 111, what we have now is that K is a normal subgroup of G1. And that gives us exactly what we needed, right? That's what we set out to show. So if G1 and G2 are groups, and H is a homomorphism between them, and we look at the set of elements that get mapped to the identity element of G2, then this set turns out to be a normal subset of G1. The significance of that is that I now know that I can talk about G1 mod K as a group, right? This is the set of all cosets, remember? All cosets of K, and these form a group under coset multiplication, or set multiplication, if you like. Right, that's exactly what we had in our example. We looked at this set Z4 cross Z2 originally as a homomorphic image of our set Z8 cross Z2, and what we saw is that the elements that got mapped to the identity, right, the vanishing set, turned out to be a normal subgroup of Z8 cross Z2, and its cosets turned out to be isomorphic to Z4 cross Z2, turned out to be isomorphic to the image. And so that's what we're going to do the next time, is to show that, in fact, that this set of cosets, that we can find that there exists an isomorphism between the quotient group G1 mod K and G2. This is a terribly important theorem in abstract algebra, perhaps the most important theorem in abstract algebra, and it's referred to as the fundamental theorem of group homomorphisms. We've done a good chunk of the proof of that. It all hinges on the fact that this vanishing set, in fact, is a normal subgroup. If it weren't, we wouldn't be able to talk about the quotient group. The set of cosets wouldn't have formed a group. Now we know that it does. And the topic of our next video is going to be finishing up the proof that this quotient group turns out to be homomorphic to the group G2. There was a lot there. I hope you were able to follow it. You may want to review this video a couple more times to make sure that the details are solid in your mind. Next time we'll finish up the proof of the fundamental theorem. Until then, stay well. I'll see you then.